give me some tutelage on what I should and shouldn't be doing. Anyway, okay, so the first process we're going to consider is it AB? It's AB. Oh no, I'm sorry, we're going to do two simultaneously. So the first thing we're going to consider is AB scattering into AB. Okay? And then we're going to simultaneously consider A scattering into a pair of Bs. Okay? So we've got two processes. One is AB goes to A plus B, and the second process is an A and an A combined to give a B and a B. Okay? Now the first thing that I want you to do is I want all of the groups to write down the two lowest, or to draw the two lowest order diagrams for each of these. There's two of them in each case. So I want you to draw the diagram that realizes this with the fewest number of vertices. Okay? And let me know once you've got those diagrams.
You got this.
All right. I know, right?
You can act like fade in, fade out, have some lens flares up in there.
I think I could make it work.
I like the fade in thing. Like, but do it really shitty. Like little squares.
Hey, Ali, you're on camera for the world. Don't drop S-bombs, and really don't drop F-bombs.
Start with AB and end with AB.
Look at these students.
Have to start with AB.
Okay, so they're going to be the same thing. We don't really need to work both.
Can we just make the first grade?
We don't really need to work both. It's the same thing.
Easy squeezing. That's a big bag of bagels. Okay, I'm going back over here. So Wachowski's got some stuff.
It's not my
Pretty
name.
good.
It's Wachowski. Like Mike Wazowski.
Wachowski.
No, yeah, but like, yeah, so it's like take this, but that's like different. No, rotate your head.
These are still
Martin, rotate your head 90 degrees. Yeah, it's the same thing, but like
That's the
same thing.
That's like saying if I just like make this on.
I'm so glad I just got Martin rotate your head 90 degrees on film. That's awesome.
It's just like this. That's still the same.
No, because here the P&A never combines like this. Yes, they do.
Yeah, it's
do it C. The like not in like time.
No, I don't think.
Yeah. All right. Yeah.
I had no results.
I definitely agree with this.
These are, you don't need high order ones.
Dang it. Wait, what? So the...
Okay, shut up. All right, hey everybody. Okay, I've let you struggle a little bit, and that's very good. Spencer. It's fine. Really and truthfully, we're going to eventually want to calculate these amplitudes, so I don't want to spend too much time just drawing diagrams. Your first time doing it, like, it really seems wacky. What do? Okay, so I'm going to give you the answers to these two diagrams, and then the good news is we're going to have 4 diagrams, and that's 1 diagram each for you all to evaluate. Okay? So to start with AB goes to AB, well, we know that we have... Sorry, I don't have an eraser. Somebody throw me an eraser. Phone a friend. See, the thing is you look absolutely badass when you don't try. You're just like stoic and cool, but if you try and fail, then you look like a loser. So don't ever try. That's the story. Okay, so when you're drawing these diagrams, the first thing to do, which I saw a lot of people doing, is just draw the external legs. Right? Because then you're just trying to fill in, you know, what can connect these and complete the story. So the first thing I notice is if I come here, I can actually bring this A and this B together. And I know if I do that, I don't have a choice. I have to spit out a C. Because this is the only vertex I can draw. It's got 3 lines coming out. One's A, one's B, one's C. But then, of course, I kind of see, oh, look at this. Hey, hip, hip, hooray. I've got that guy right there. Okay? Now, Oh, I was like, that's the weirdest muffling clapping I've ever heard. Yeah, I drew that diagram. Okay, so now the problem is, you're probably staring at this going, well, there's not another way to do this with two vertices. Okay, but if we actually think about starting with this picture, then we start thinking of a possible different diagram, right? And that is, I can connect this A to this B, this A to this B, and have a C go there. Okay? Now you look at that and you go, and this is an important question, are those two diagrams the same or are they different? Okay? Who is that? Oh, they're just, yeah, that ain't happened for a while. Anyway, okay. So let's talk for a moment about the physics of what's going on in these two pictures. So here, the A and the B are literally, remember time runs to the right. In this diagram, A and B are literally disappearing for some moment of time, and there's only a C. And then that C disappears, and then an A and a B emerge. However, in this diagram, there's always, at all points in time, an A and a B in the story. Now that has kinematic consequences because, for example, here, the momentum in particle C has got to be the total momentum carried by A and B. So that's going to give some kinematical information about what's going on with C. Here, though, the momentum in C is not going to be A plus B. It's actually going to be the difference in them. It's going to be how much momentum A is giving to B, or vice versa. So in thinking about whether these are different diagrams, it helps to actually sort of think of the kinematic consequences of the pictures you're drawing. All right? Now, with that in mind, can anybody look at this picture if I had insisted on starting with these external lines? Can anybody look at that starting point and see how we would have ended up constructing that diagram? So it's a weird picture to draw, but let's just do it. So we know what we're doing is we're somehow flipping these two over. So what we could do is we could have this guy come up, and then him come down, and then this guy would actually come and hop over this and come down here. Now I draw this because if you think about it for a moment, you'll realize that is the same picture I drew before. Okay? So occasionally you have to let two lines cross, and just to make sure that you're not calling it an interaction vertex, because I don't want this line to intersect this line at a point, because that implies interaction. I just draw the little hop over sign. Okay? Now the reason that's useful is because when you're trying to enumerate all the diagrams in a picture, it's very useful to always draw the same starting and ending external lines, and do not allow yourself to permute them around, because then you might end up drawing more diagrams than you should. Okay? Now with that in mind, let's come to this process. So can anybody point to I see a diagram back there for this process, so let's go ahead and draw that. So I have an external A, an external A, an external B, an external B, and then I can just connect it like so with a C. Okay? And now the question is what is the other diagram for this process? And that's the hard one. Does anybody have a guess? What other second order diagram is there for this process? You actually, you're very close to it, actually. No, it's fine, it's fine. So, actually, you know what, that might actually be the same thing, okay? So the way that I usually draw it is like this. So I start with the diagram that we began with, okay? And then what I do is I switch these two outgoing B's. Okay? Now, you might say again, well, are you allowed to do that? Is that a physically distinct diagram? And here's the thing. in this case, first of all, I can switch these and they're both still B lines. Okay? But when I go in and I actually label these diagrams to compute the Feynman, the amplitude from the Feynman rules, what I'm going to find is that the momentum of this B is related to the momentum of A by how much it loses from C. Whereas the momentum of this B is a combination of this momentum coming in and what it loses or gains by C. Now you might say, well, why does that matter? Well, when we do the Feynman calculation, each of these external lines gets their own distinct momentum label. So right now when you look at this B and this B and this B and this B, they kind of look the same, but we're actually going to label them with distinct momentum values. And then, so maybe if this is P1, P4, you're going to decide your labeling later. But the important point is, the line up here is going to have the outgoing momentum P1. The line down here is going to have outgoing momentum P4. The outgoing line here also carries P1. Here it carries P4. But this P1 is coming from the lower vertex, whereas this P1 is coming from the upper vertex. So it's not until you start thinking about the momentum that you'll really realize these diagrams are different. Rochelle?
How come you can't like do like the same thing that you did above, but then do like the line and horizontal on the bottom?
So this.
No, like you do the cross, but then the C goes under instead of on the line.
You want to come and draw it? Yeah. Come draw it. Do it! Who's down in the house? Come on, Rochelle. Come on. Somebody's got the picture. You can do it,
No,
Rochelle.
I probably am wrong.
No. You're this is your first time showing the diagram. So
Like, what if you like it that way and then the C there? And, oh.
go!
Like this. This.
Like, I guess it's kind of like a B here, and then a C there, and then a jump, and then a C there.
So yeah, so that's so okay. So if I take this thing and I grab this vertex and I literally just in space move it up here, that's the diagram I just drew.
Oh, okay.
Yeah, so this is another skill you have to develop with Feynman diagrams is they don't actually care if you continuously deform the positions of the vertices. They don't care. So there's a little bit of topology involved in drawing all the different Feynman diagrams. Okay, Joe Bales.
So the different B's are distinguishable from each other? Is that what we're...
The different B's are distinguishable because we're going to give everything momentum labels, and the momenta are different, or can be different generally, so we want to distinguish them. Okay, so, all right, hey, look, so we're going to do more complicated examples in a few minutes, but what I want to do now is have the groups of 4 each evaluate M for one of these diagrams, and I'm just going to go around the room. This group gets this diagram. You guys get this diagram. You all get this diagram. And you ladies get this diagram. All right? And I said guys. I'm not going to just, guys, ladies. All right? So go for it. The rules are written up on the board. I want an expression for M at the end of it all. Oh, there we go. You can, yeah, there we go. Talk about that time, baby.
Yeah, so see, you can see this is the time axis. So these, I'm spying on him, which is him, by the way, the dumbass. I'm spying him back in time. And then he's, for some reason, in the future, but he should be in the past. But that's fine, man. He likes what we did.
Okay, all right, sweet. Good job, guys. Have we got an answer down here? Yeah. We do? What is it?
It's G squared over P1 minus P4 squared.
Is that good? Did you do it?
It looks good. It looks good. Awesome. Awesome. Okay, we got an answer?
Yeah, we do actually.
Let's see it. Oh, nice. Let's get a little snapshot there. Good job, guys. And last but not least, have we got one? Ashley, are we there? Oh, I'm going to get her writing it.
close. We killed you. On either side.
That's not what I wanted. Nice.
I can't focus on the pink. Oh, she did a marker drop. She totally did a marker drop. Okay, sorry that got off us. Record this because it's so awesome to make recording. Anyway, okay. Now we are going to consider a different process. This time we are going to consider A decaying into a B and a C. So we led with this process last time. Does anybody remember what the lowest order diagram is? You get 0.1 seconds. It's just a vertex that connects these. Okay, I evaluated that for you last time. Guess what you guys get to do? You get to do the next order. So, to remind you, the next order looks like this. There is the vertex correction. Plus the self-energy corrections. And I'm not going to label these because from the picture it should be clear what the labels have to be. Okay, it's always going to be A, B, and C, okay? And then we're going to go the opposite way around the room. So this group gets the vertex correction. Group in the back gets the self-energy correction on the incoming particle. This group gets the self-energy correction on the upper outgoing particle, and this group gets the lower. All right? Go for it. I think I just turned this off, so maybe it's been a waste. Anyway, it doesn't matter. It's good B footage.
Get rid of the 2 pi to the 12.
So we do these 2 integrals.
Are you one of those groups that canceled all the 2 pi to the 4s?
What? No.
Well, why don't those delta functions have 2 pi to the 4s in front of them?
This one's not done. They're over here.
Oh, why'd you do that?
Because they're all 2 pi to the 4s.
But I know, but you're going to remove a 2 pi. You're always going to be removing a 2 pi to the 4 and a delta function simultaneously. So that's why it's good to keep everything kind of right next to what it's paired with. And then the same with the DQs over 2 pi to the 4. You'll erase that whole factor.
Okay, well,
so
this first one we canceled 1, so now we have that.
If you don't want sloppy whipped cream,
anyway, so what we do with these things is, so I'm going to, for example, remind you that in the case of 2-body scattering, and I have my other sheet up here. Let me get it from over here. In the case of 2-body scattering, where we just have 2 bodies come in and 2 bodies come out, then the scattering amplitude expression simplified. So in the CM frame, we have an expression for d sigma d omega. And you guys let me know if I forget any factors of pi anywhere. But in the center of mass frame, the expression for d sigma d omega is h bar c over 8 pi squared times the permutation factor times the magnitude, or the amplitude squared over E1 plus E2 squared over the ratio of the magnitude of one of the final momentum to one of the initial momentum. Okay, so we've done a 2-body scattering process. You know, we looked at a couple of them, but in particular we looked at AB goes to AB. And we calculated the amplitude for that. Oh, my arm's getting tired holding this heavy marker for so long. It's crazy. And we just calculated the amplitudes for that, and what we found was that M gets 2 contributions. There's G squared over P3 plus P4, where the P's are the amplitude, sorry for that. So the amplitude has 2 contributions. You're killing me. And see, what this is my way to make sure you all listen to me finish. Okay, so what will we do in this process? Remember, these are all labeled with momentum values, and I can't, this is P3, yeah, P3 and P4. Okay, so if I wanted to calculate d sigma d omega for this, I would literally just take all of these factors over 8 pi squared Okay, S, does anybody remember what the factor S is going to be in this case?
Your mom.
Whoa! Do you know that my mother has 9 sons?
Did your mother
You don't talk about my mom. My mom will kick your butt. Okay, so what is the factor S here? Pretend to the world that I actually taught you something. What is S?
It's to get rid of your number of identical particles.
Yes, it's 1 over a factor of, it's a permutation factor for every number of identical particles either coming out or going in. But the good thing is that A and B are distinct. So the S factor is just 1 in this case. It would be non-trivial in the case where we had AA go to BB. Okay? So S is just 1. We have our expression for M. Okay, so you can just plug that in here. And then here we have E1 plus E2. And then here I could just say one of the final particles, it doesn't matter, call it P3. And one of the incoming particles, it doesn't matter, call it P1. Okay? So this is what we would actually do with the quantity M that we've calculated if we wanted to get something that we would go take to an experimentalist and say, hey, go measure the differential scattering cross-section for AB scattering into AB. Okay? On the other hand, if we were considering the decay of A into, say, B plus C, this is a 2-body decay process. And for a 2-body decay process, we have a particularly simple expression for the decay rate, which is given by S times the momentum of either of the particles coming out. It doesn't matter which one because, in the rest frame of A, these come out back to back, divided by 8 times h bar squared.
Professor, I think you're missing. Hey, Alex.
What?
I think you missed something.
Oh, I'm missing a pi.
I got the pie, don't worry.
So what you would do with your expression for M, which you guys just calculated on all the boards around the room. So remember, remember that M is G plus horrible stuff. All right, where horrible stuff, that leading order is. Horrible stuff are the 3 or the 4 higher order. No, wait, listen, it gets gooder, okay? Because you guys were too lazy to evaluate those integrals. But what you get to do is you get to take all of those things and add them together and then square it. Oh yeah, I know, it's pretty bad, okay? But nonetheless, in this process, what would our S factor be?
1.
It would be 1 because the outgoing particles B and C are distinguishable. You could just put in, if you were assigning these P1, P2. There's stuff everywhere. It's gross. The P here would be one of the P's, so this would be 1 times, just call it P2, over 8 pi h bar squared, M1 MA squared, C squared times your expression for M squared. Okay? And then what you could do is you could take this and go to an experimentalist and say, hey, here is the likelihood of observing particle A decay in particular into the combination B plus C. Okay? And this, of course, I should reiterate, is a decay channel. It's one particular set of outputs. If we wanted to actually calculate the total decay rate of this, God, I thought she was coming in with another time. If we wanted to calculate the total decay rate of A, what would we do?
You sum all the possibilities.
I look at all possible things that could come out, calculate gamma I for each of them, add them all together to get the total gamma. Okay? And that's what I would actually have to do if I were interested in calculating the lifetime of A. Because the lifetime of A doesn't care what it's decaying into, it's just saying what's the probability of it decaying into anything. Okay? So with that in mind, this is a good look. Are there any questions before we bug out of here? All right, you're all free to go. I'm not going to give any homework over spring break, so I'll see you on Tuesday, the week after, where we will talk about quantum electrodynamics.
Hey, Alex.